Hello, welcome everyone. Let me know if you can hear me. Welcome to this Sunday YouTube session. We're going to be looking at differentiation. Feel free to say hi in the chat if you haven't already. And yeah, good to see people here already commenting and stuff. So welcome, hope everyone's keeping well. And we're going to get started shortly. So feel free to say hi. I've got the chat open so I can see any messages coming through. So welcome. Right, let's have a little look. It's lovely. Cool, so we're going to be looking at differentiation today. And hello, welcome guys. This is a topic really kind of crucial. Calculus is really crucial to the A-level maths and starts kind of at the point in year 12 we start looking at it. So it'd be great to hear questions and answers as we go. And this might be a new topic for some people, and for others it might just be revision. But this is a part of calculus, and this is something we often start quite early on in year 12 as part of the pure maths. Hiya, welcome guys. I'm going to share my screen now and we'll get started. Let's just make sure we can all see what I'm about to share. So differentiation we're going to look at, and hopefully this PowerPoint is sharing now. And I'll just make sure I can still see all your comments, questions and answers as we go. Hiya, welcome. Hi, lovely to see the comments coming through. I hope everyone's well and having a good weekend. We're kind of cracking on through the first term back of the academic year already. So lovely, great. Right, so we're going to get started. And as I said, I'll be talking a little bit about Snap Revise towards the end, but we're going to whiz through this differentiation topic, the kind of key ideas surrounding differentiation, which for a lot of people at A-level is a new topic in year 12 and in year 13 as well. So it'd be lovely to hear if this is revision for people, if you started it, or if this is brand new. Feel free to let me know in the chat to give me a sense of who's covered this before. So yeah, obviously differentiation does grow and it gets a bit more involved. And I'll talk about the web classes and sessions we've got and recordings and resources that can help you with that on the platform towards the end of this session. But let's get cracking with this topic. So I'm going to share the screen. I'm Max, I'm head of maths at Snap Revise, and I did my maths degree a few years ago and then went straight into teaching. And I've been teaching A-level maths, GCSE maths and below for the last sort of 4 or 5 years. So it's been an interesting time to see things change and the new qualifications come in as well. What we've got a discount today, so a back to school offer. This code I'll talk about towards the end, which is useful for if you'd like to kind of do a trial on the site, see what other resources we have to offer, and I'll talk about that, as I said, towards the end. So stick around for that and we'll come back to this bit. That's great. So let's look at what we're going to cover today, and that should hopefully answer some of the questions. We're going to understand what a derivative of a function is, what differentiating a function actually means. Differentiate simple polynomials, and then look at the trickier indices and trickier powers. I'm not going to do differentiation from first principles. That's kind of another subtopic, a different video, different web class. And I won't do the kind of trig, exponential and logarithmic differentiation. That's more sort of year 13. But again, we've got other sessions on that. I'm going to look at the real principle, the kind of basic ideas behind differentiation and how to carry it out, and that should hopefully be a good start for everyone. So let's have a little look. Apologies if I miss any questions. We'll have a bit of time for questions as well at the end, so I'll try and backtrack if I've missed anything, but please do get answers and questions in the chat, and I'll do my best to go through those. But yeah, let's get straight on with this. So let's talk about what differentiation is. So it's an important part of calculus. So yeah, all of those harder rules stem from this quotient, chain and product. That all kind of comes from what we're going to learn first of all here. So to start with, a gradient, hopefully we've learned at GCSE, and we're quite confident, is to do with a rate of change. So if we imagine on a linear function like this, we have an output there, let's call it y2 and y1, and an input value x1 and x2. Some people just happily to remember it as the gradient is the change of y over change of x. So it's effectively y2 minus y1 over x2 minus x1, rise over run, change of y over change of x. And for something like this, that will come out as a number. that will just spit out a value because we know that has a constant gradient. It's a straight line. Now, what's weird with differentiation is if we look at something like x squared and we try and talk about the gradient itself, the steepness, is actually changing the whole time. So that's where this becomes really useful. So if we look at the curve here, the gradient here is 0 at this turning point. So the gradient is 0. And then here, it's like a positive gradient. And then up here, it's like an even steeper positive gradient. So it kind of gets steeper. So this is what we're dealing with differentiation. We're dealing with a gradient that's changing. So it gets steeper that way. And it kind of gets steeper in a negative direction. So on this side, the gradient of the quadratic or the parabola is negative. And this is what we deal with. And it's a really nice kind of technique once we know how it works, and quite useful for doing a lot more with graphs than we would have seen at GCSE. So the gradient's positive, the gradient's negative, and it's kind of getting steeper as it goes. So I went to King's College in London and did my maths degree there, and then went into teacher training after. So that's like a little bit of background. And as I say, this topic, differentiation, calculus, is something that kind of saw me through the degree as well. Like, this is such an important, crucial part of anything you're going to do with maths or any maths-based degree and science. This rate of change and understanding rates of change is crucial, and it really does evolve. So this skill, of course, is on all the different exam boards. So whoever you're doing the A-level with, whether it's EdXL, OCR, or AQA, this will definitely be on there. Calculus is so fundamental to the A-level, and this is the real kind of core start to it. So really, really crucial topic, which is why we've chosen to look at this today. So I'm going to talk about the background of it, the derivative of a polynomial. So for example, the derivative of the function f of x with respect to x is basically defined as the rate of change of f as x changes. And there's two little ways to denote this. So we're going to look at the notation. So if they use the function notation, we denote the derivative as f dash of x. Or if they say y equals something to do with x, the notation is dy dx. So these two things, f dash of x with a little prime at the top and dy dx, they mean the same thing. They mean you differentiate it. And we call that process when you differentiate something the derivative. So if we have a function and we differentiate it, we use f dash. Lovely. Yeah, absolutely. So that means the derivative. And if they use y, to be consistent with the notation, we use dy dx. So we'll see some examples to make more sense of this. And the derivative of function at any point can be found from its graph by basically finding the gradient of the tangent. And they kind of ease this into GCSE a little bit. Sometimes it's in one type of question. Find the gradient of the tangent. Who has done that skill before at GCSE? Because that was very new to the GCSE, that they make you sort of draw a tangent on and look at its gradient. So finding the gradient of the tangent at that point, that's the kind of graphical way, but it's a little bit clunky on paper to do it that way. So we're going to find a nice, really simple and straightforward algebraic approach. So you're finding the gradient of the tangent at that point. So here, the gradient is quite clearly positive. So f dash of x would be greater than 0. It would be a positive number. And here, the gradient is actually flat. It flattens off. So here, f dash of x would be 0. The rate of change is 0 temporarily. And then it's a positive gradient again. And that would be like evolving and changing. So what we're going to do is we're going to look at a really formal and simple way of doing this now. And the process is called differentiation. So I'm going to move that on, but do feel free to ask any questions or backtrack. To find the derivative, to differentiate, here we go. It's a really straightforward rule, and you're going to pick it up in no time. So what we do is, if we look at something, x to the power of something, there's just two easy steps. So the first thing we do is we multiply by n, and then reduce the power by 1. Excellent. Right. Good. I'm just trying to keep an eye on the chat as well. Lovely. Power by 1. So this will be a really nice start for everyone to give it a quick go. X squared, if we differentiate x squared, we times by the power, so times by the n value, the 2, and then drop the power. So x squared would differentiate to 2x. Lovely. So let's whiz through. We'll go this way. Let's differentiate these. So x cubed, can anyone tell me what that would differentiate to? So we times by the power, reduce the power by 1. So the derivative of x cubed would become what? So we're going to times by the power, drop the power by 1. So that is called differentiation, and we're finding the derivative. So that would become 3x squared. Brilliant. 3x squared is the derivative of x cubed. Next one, x to the 4. And you might be thinking, okay, this looks okay. Same process. Times by the power, drop the power by 1. So that one will be 4x cubed. Lovely. Well done. And then the next one, so we're going to keep going. And this is where we're looking at all different polynomials and all different powers of x, where they're whole number powers at the moment. So this one, absolutely right. We're going to have 5x to the 4. Next one, hopefully quite straightforward as well, 6x to the 5. Thank you guys for sharing answers in the chat as well. That's lovely. The next one up here, the derivative of x. So what do we reckon? Yeah. So think of this as x to the 1. The derivative of x to the 1. That would become 1 x to the 0. Now, x to the 0 is 1. 1 times 1. So that just differentiates to 1 because it will become a constant. Hopefully that's clear. Yeah. Now, a constant like 1, I would think of that as differentiating like 1x to the 0. Because if you're thinking, how do I write 1 as a power of x? Well, it is kind of like 1x to the nothing. Then you times by the 0, it just goes. So if you differentiate a constant, it goes to 0. It's not affecting the gradient. It's not affecting the rate of change. Okay. So the next one here, again, same process. Times by the power, reduce the power by 1. So 64x to the 63. Lovely. Absolutely. And then we keep going. The next one, 99x to the power of 98. And we will kind of put a bit of context on this in a minute. I'm just trying to get everyone in the process of being able to do the differentiation. So then the next one, yeah, very good. Lovely. You can see the answers coming in to the 255. Cool. So hopefully we've got that. And yes, just for clarification, as we said, any x to the 1 just becomes 1, and any constants will go to 0. Absolutely. Brilliant. Right. So I'm going to keep going. We're going to make these slightly trickier and look at obviously bigger problems that involve this now. But this is effectively the process to start with. We deal with much more involved functions as the course goes on. But for polynomials, this is all we do. Times by the power, drop the power by 1. And we can do a lot with this derivative. So it is really important. Right, let's keep going. So there are 2 key rules which make differentiating a lot easier. They're quite nice rules. If you have a number times the function and you differentiate it, it's still just that number times the derivative. Okay, and likewise, you can differentiate multiple things and you just do them all separately and put it all together. So we'll see with an example. So here, if this is the thing I want to differentiate, notice that we've used the notation y. So we use dy dx. If they'd said f of x, we would use f dash x to denote that we're doing the derivative. So the process of differentiation, and what we do is we literally just differentiate each bit. So 10 is like 10x to the 0. That bit will become what? When I differentiate 10, when I differentiate a constant where x is effectively to the power of 0, what happens to it? And wow, well done if you've whizzed ahead and done the whole thing. I'm just going to talk bit by bit just for this one. That one is 0. This 3x to the 1 will become 1 times 3x to the 0. So 1 times 3. So that bit will become 3. The next one, times by the power and drop the power by 1. So 2 times 4x to the 1. So that will become 8x to the 1. And what we've used is we've used this rule. because the 2 gets times by the 4, and then I drop the power by 1. So 8x, very well done if you got that. Next one, I'm going to times by 3, so minus 15x to the 2. Then I'm going to times 7 by 19, which is 133. And then I'm going to drop that by 1. And that's it. That is the derivative of the whole thing. So I just differentiated each little term separately, and that's the function I come out with. That's the derivative function. So hopefully that was nice and clear, and very well done if you shared answers and you followed that. So please do ask, though, if any of that wasn't clear, and we'll look at how this evolves. So very well done. That was great, and that's a nice start. We can now differentiate a polynomial. That's the skill done. Brilliant. So what I'm going to do here is I'm going to move this on, just pause for a second. And if you guys can just let me know in the chat, just a 1, 2, or a 3 on how confident you're feeling. Welcome if you've just joined. We've just introduced this idea of differentiation. So just give me a sense of how you're feeling about this so far. It might be that for some people this is brand new, and for others this might be revision. This might just be you're checking over a skill you've done before, and you're perhaps looking at the next thing. But just give me a little indication of how you feel about this topic so far. Brilliant. Okay. So I'm going to just look to move this on. So this specific part is covered at AS level, but the topic itself grows from here. So we're going to look at exam style questions now that carry on, because what's quite nice about this is in the A level part, the year 13 part of the course, it's the same types of questions, the same need for doing differentiation, same style of question, but just a little bit more involved. So that's lovely, and thanks for sharing answers. That's brilliant. Let's keep going. So find the gradient. Here is a typical exam question where we would use differentiation. So find the gradient of the curve y equals 2x squared at the point where x equals 3. So this is what differentiation's for. Like, this is why we do it. So we're going to have a little look. The first thing we're going to do is differentiate it. So we've got y equals 2x squared. So what is dy dx? Dy dx would be what? What is the gradient function of that curve? So yes, you do, just in answer to that question. Absolutely. You do all crazy sorts of differentiation as it goes, and you will do it for trig and other functions as well. But this is sort of the first bit. So the derivative is 4x, and I would show that working. Now, the way, I think some of you have already done it, the way we evaluate it when x is 3 is we sub x is 3 into that function. So that means that dy dx would be equal to 4 times 3, which would equal 12. So it tells us that that coordinate on the 2x squared graph when x is 3, if I plug it into the gradient function, the derivative, it spits out 12. It tells me at that instantaneous point on the graph, the steepness is 12. That's what differentiation is for. So when you differentiate a function, you find its gradient function. You find this sort of mechanism for working out the steepnesses at any point. So it is really cool. Like, the thing you're working out is like a steepness machine. It's like a rate of change function that you put the input in as the x value, and it tells you what the steepness is doing there. Absolutely. Feel free to ask any questions as we go, and I'll do my best to answer. Right. Now that we've got that function, this function is crucial. This gradient function here, dy dx being 4x, this is telling us what the steepness is doing of the curve. So it's following this thing. It's doing its own thing, the steepness. And I've worked out what's happening when x is 3. Now, it says in part 2 of the question, as some of you have looked at already, at a point A on the curve, what y equals 2x squared, the gradient of the normal is 1/8. Find the coordinates of A. So who can tell me what a normal is? So the normal line, you might have seen this in the earlier chapters, you might have met it before, the terminology, the normal. It is, yeah, very good. It's kind of like opposite to the tangent. It's the perpendicular line to the tangent. So it sort of chops through the curve at 90 degrees. So that would be the tangent. And then at 90 degrees, that would be the normal. So the normal basically cuts through the curve at 90 degrees. So that would be the normal line. So what we hopefully know about graphs and perpendicular lines is that if that's the gradient of the normal, then the actual gradient of the tangent and the function is the negative reciprocal of that, because it's perpendicular. So perpendicular gradient to an eighth is -8. Do we all recognize that thing? Like you might have hopefully seen that before this topic, that if you have a perpendicular line, then it's the -1 over the gradient that you have. So it's the negative reciprocal. It's like the flipped and you change the sign. So that's actually like a complicated way of telling us that the actual gradient of that curve at that point is -8. So what we know is that dy dx must equal -8 at that point on the curve. So I'll talk about it a little bit more in a graph context, because I can see that would be a lot more clear visually, like to look at it in that way. So I'll just have a little look. There's a lot of these questions don't always have a graph. So I'll speak a little bit about that later, but we'll do other videos where we look very carefully at the graph work. But yeah, that was a really good question. Let me just carry on with this one and then we'll see how we go. But yeah, brilliant point. So what we're going to do is we're solving when is that gradient function equal to -8. So x would be equal to -2. And then you think, great, I've solved it. Just be careful as well that it did also say find the coordinates of a function to get the y value. So what we would have is we would have the coordinate would be -2, and then -2 squared is 4 times 2 be 8. That would be the coordinate of A. Is that all right for everyone? Does that make sense? Is that all okay? Yeah, brilliant. Okay, cool. Right, we'll keep going. So we'll do another exam style question and then we'll move on to the next bit. So here we go. Now we've got a function here. Given that f of x equals x plus 1 squared times 3x minus 4. So part I is not differentiation. It's just like expand it, basically. So part I is a little bit tedious, but we want to expand it so that we can then differentiate it. So if I expand it out, I'd probably do the double brackets first, the sneaky double bracket, x plus 1, x plus 1. Be very careful, because I've seen so many students rush this and just square x and square 1. That's saying a double bracket. There's actually 3 brackets to expand here. So this would become x squared plus 2x plus 1. Then that's all getting times by 3x minus 4. A little bit of a tedious question, but you're picking up some marks. That's lovely. I'm glad to hear that. And I will try and clarify a few more things as we go. And we are going to look at a few sort of slightly trickier examples as well. So that's great. Right, let's expand this out. So this would give us 3x cubed. So we just got to remember to times all the bits together. That's why it's kind of tedious. 3x cubed minus 4x squared plus 6x squared. Oops, sorry, my pen went a bit weird there. 6x squared minus 8x plus 3x minus 4. Check I've done that right. I think we're good. Yeah, and that will all tidy up, hopefully, to 3x cubed plus 2x squared minus 5x minus 4. So that's the expanded version of f of x. Now it's asking me to find f dash of x. It's asking me to differentiate. We want the derivative. Is that okay? Am I all good there? Yeah. Cool. Yeah, cool. Right, so differentiating it then, we're going to get 3 times 3. So we're going to get 9x drop the power by 1. 2 times 2, 4x drop the power by 1. Don't really need to write that. Minus 5, x to the 0. Sorry, x to the 1. So times it by 1, minus 5, and the x will go, and the constant will disappear. So this is the derivative. So this is the gradient function. This quadratic function describes what the steepnesses are doing of this cubic function. So it's really cool that we've generated a function that happens to be a quadratic, that when you plug a number in for x, tells you what the steepness is doing for that cubic function it came from. So it's a really, really powerful little skill that tells you a lot about every point on that graph. So really important. Lovely. So let's keep going. Right. Hopefully we're good to move on. Let's now look at differentiating reciprocals and roots, which is a little bit more involved, but it's the same skill. So the way we're going to do this is to actually think of it as powers of x. So when you're going through the course and you start those first, no worries, I'm just checking some of the earlier comments, that's fine. Where I'm looking at the rule, remember it relates to it being in the form x to a power, x to some power. So if it's not quite written like that, that's why we have to be good at manipulating indices and manipulating the algebra. That's why the earlier chapters of the A level are designed to recap that sort of stuff. So it might be that some of those early chapters you think, oh, this is really tedious and boring and just playing around with algebra. It's really so you're able to make sure you can do this. So can anyone tell me how I could represent this x to the n, 1 over x to the n? Absolutely. I think some of you beat me to it. This is going to be x to the power of minus n, or 1x to the minus n. So if you're confident at doing that, this is now in a much more user-friendly form for us to differentiate it. So that would mean what we would do is we would times by it. So we get minus n x to the minus n minus 1. So that would effectively be minus n over x to the n plus 1. Because remember, if this was like minus 3, then it becomes positive 3 on the denominator. So hopefully that sort of little rule makes sense. Yeah, exactly. Good. So let's do some examples. So if I have the derivative d dx of x to the minus 1, I times by the power, drop the power by 1. That'd be minus 1 x to the minus 2, which is effectively minus 1 over x squared. Is that okay for everyone? We all all right with that? Just check. Well, that's all clear. Yeah, minus x to the minus 2, which we can write as a fraction like that. I'll express them as fractions just so we've got both forms, but don't worry, like it is the same thing as we've said. Yeah, good. So some of us are whizzing ahead. So this is, first of all, let's think of it as the derivative of x to the minus 2. Times by the minus 2, drop the power by 1. So that's minus 2x to the minus 3, which is the same as minus 2 over x cubed. Brilliant. Now this one here, what are we going to get here? Yeah. So we're going to get, this is 13x to the minus 13. Multiplied by the power would be minus 169x to the minus, let's be careful, minus 14. So that's minus 169 over x to the 14. The 4 to the 14, there we go. Now, same thing again. Don't let this put you off. We can tidy this up actually quite easily. So we're dividing everything by x squared. Well, then that's going to mean that this is just a complicated way of writing x plus 4. And remember, because you can think of all of these separately over x squared, can't you? And cancel them down. And so x cubed over x squared is x, 4x squared over x squared is 4, x over x squared is 1 over x, or x to the minus 1, even better, and 5x to the minus 2. Now it's ready to go. So let's do that. So the x differentiates to 1, the 4 goes, so you can actually leave that bit, minus x to the minus 2, minus 10x to the minus 3. So that's what we got. That's where we're at. That is the derivative. That is the gradient function of this thing. Okay. So it was worth looking at negative indices because, of course, we could have that. We could have worse. And that's what we're going to look at now. So let's have a little look at this time looking at roots. So when we've got a square root of x or an nth root of x, hopefully everyone's happy that this is a power of 1 over n. And just a good way to little sidetrack and remember why this is a rule. Remember, guys, if you think about it, y is x to the half root x, because x to the half times x to the half is x to the 1. So when does something times itself make the number? They would have to be the square root. Okay, that's because some people learn it as a rule and then they confuse it with reciprocals. And I was never really explained like why that is the case. But because of power laws, a half plus a half is 1. So that thing must be the square root. So just if you struggle remembering that fractional ones are roots, that's a good little way to remember it. So the nth root would be like this one here. The derivative of this would be the same as the derivative of x to the 1 over n, which would be 1 over n to the x of x to the 1 over n minus 1. And suddenly, even as a formula, that's starting to look a little bit nasty, but it's not. It's the same process again. Let's just do it really carefully. So here we're effectively being asked to differentiate x to the power of a half. So to do that, we're going to get a half times by the power, drop the power by 1, x to the minus a half. There we go. This one, let's be very careful. X to the third. Can anyone tell me what this becomes? Be really careful, especially subtracting 1. I know that sounds a little bit silly to say, but so if I times it by a third, it will be a third x. Good, well done. It was x to the third we're differentiating. And when we differentiate, we'd have a third x to the power of 1/3 take away 1 is actually minus 2/3. Well done. Because if you take a third away, you get back to 0. And you've got another 2/3 to go into the negatives. Very well done. Thank you guys for sharing answers there. These are the kind of ones where it's like around 0 and you're taking away a fraction. It can go a little bit wrong. So just be really careful. This one here, let's just look at how we would express this. This is asking us to differentiate. Basically, be really careful. This is all squared. So this is actually a complicated way of writing 4x to the 2/3. Do you see that that's really sneaky, that 2 is squared as well? Yeah, you do indices. If you're thinking big mass or bod mass or whatever you called it, the order of operations, the bracket is first and the bracket is raised to an index, but it's all squared. So 2x to the third is being times by 2x to the third. So you're going to get 4x to the 2/3. Is everyone clear on that is a complicated way of writing? Then I can just do the same process. Times it by 2/3, drop the power by 1. So 4 times 2/3 is 8 8/3. There we go. X to the minus 1/3. Is that all right? Yeah. So this is kind of these kind of questions will be in there. This isn't like trying to be mean or trying to make really ridiculous ones. This will be, you will be asked to differentiate functions that you couldn't even necessarily know what it looked like as a graph. They will ask you kind of these weird kind of harder scenarios. So yeah, it does get very involved. And because you might think, well, why would I ever want to do that? But the questions could deal with really kind of crazy graphs and mathematical functions and models that you need to then go, well, can I still find out the rate of change at this specific point? So yeah, it is, because it's such a huge topic, it does go kind of quite difficult quite quickly. But what I'm saying is, even with these, if we're careful, it is still the same process. But the big important thing is to be aware of the pitfalls and like know where you could easily trip up, because we can all make these mistakes if we're rushing. They're tidying it up and actually going through this process is really worthwhile. But yeah, brilliant questions. So again, this is a bit like the other one in that let's just write it in a simpler way. X squared over x to the half. Now, if you think about it, just use power rules. X squared over x to the power of a half, you subtract, don't you, when you divide? So 2 minus a half is 1.5. So this is basically y equals x to the 3 over 2, because we can rewrite that as x to the half and then just subtract the powers. So 3x to the 1 over x to the half will be 3x to the half because I'm taking away the powers. And then the next one, x to the half over x to the half, is 1. And then this next bit will be 9 over x to the half, or 9x to the minus a half. Now, apologies if that was a bit quick. Do let me know if I need to clarify any of those. But this is important that, obviously, you know, if you rewrite it wrong, then when you differentiate it, it'll be wrong. So just be really careful on that we get everything in terms of powers of x. So times in it now, 3 over 2 times x, so 1.5, x, and minus 1 from that power would be a half. And then 3 over 2, x to the minus a half. The 1 is going to go because it's a constant. And then this would be minus 9 over 2, x to the minus 3 over 2. Is the sound all right for everyone? Apologies if it's cutting out or it's not clear. Let me know if it's like lagging or anything. It sounds like for some people it might not be clear. Oh, good question. So integration is the second part of calculus. I would say yes, in year 13 particularly, but I would say what we notice as the course goes on, for integration, it becomes based, it's about how well you know the differentiation. So if you don't know the differentiation well, you won't be able to do the integration in year 13. So the nice thing of that is that it revises differentiation, because in year 13, there's a lot of comparisons and using what you know about differentiation to help you. So I would say it's very much tied in, but it's, as we said, a huge part of the course. So I would say at least the thing to look forward to about it getting more difficult is that at least when you do integration in year 13, it sort of recaps your year 13 knowledge of differentiation. So yeah, it's certainly the biggest probably chunk of the A-level course. Cool, lovely. Right, so little checkpoint, guys. If you can give me an indication of how we found that. We'll do an exam style question to see like a few of these in terms of exams. I'll try and talk briefly about the graphs, because it is a very graphical based skill, but we've looked at it from this point of view today. Lovely. So yeah, just a little indication if you haven't already. Thanks to those that have suggested it's going okay. That's good to hear. Lovely. No worries. Brilliant. Great. So I'm going to move on. Let's do an exam style question. And for this, I think I'll give you a few minutes to have a little think. Brilliant. Right. Lovely. That's great, guys. Thank you for working so well up to here. Let's have a look at this now to kind of round off the practice. Let's differentiate these and see if we can work them out. And yeah, welcome if you're joining as well. We've kind of looked at differentiation here. I would also say that the okay, right. I would also say that there is the calculators you can use for this course do carry out differentiation at a specific value, but a lot of the questions you have to show the working for A-level to get the marks, but it's good to know you can do that to check your answers. So I can talk about that as well. First one, let's differentiate it. Yeah, well done if you already have. Let me give it a go. So f of x is x plus, and I would rewrite it as 3x to the minus 1. Then we can whiz through and differentiate it. X differentiated is 1, and this would be minus 3x to the minus 2. Brilliant, which is the same as 1 minus 3 over x squared. So that's great. Well done. Then the next part says find the gradient of the curve y equals x to the 5 over 2 at the point where x equals 4. Well done if you've done it. What I might do as a little aside to kind of help you guys out, there's a really cool calculator technique for this that just does it for you. So if for those that have, I've got a Casio ClassWiz here to show you that you can do it on here, but a lot of the calculators that are allowed now can do this. So I'll show you how you can check your answer in a minute. So 5 over 2 x to the 3 over 2 is the derivative. So if we want it at the point where x equals 4, that's not y, sorry, that's dy dx. then the value when x is 4, we're going to get dy dx. Oh, that was a bit strange. Dy by dx is equal to 5 over 2 times 4 cubed. What am I doing? 4 to the 3 over 2. Yeah, so that would be 5 over 2. Now 4 to the 3 over 2 is the square root of 4, 2 cubed, which is 8. 5 over 2 times 8. So 4 times 5, basically, which is 20. So the gradient of this function when x is 4 is 20. Now, let me show you a little way to do this on the calculator. For those that have this equivalent, the class Wiz, some of you have this calculator for the A level, you can do it on here. For those that have it, if you go on, turn it on, and then under menu setup, if you press shift, there's a button that says ddx, and then like a little box, and you can fill it in as x plus 3 over x. And then where there's the little line, x equals, you can put x equals 4, and you press answer. Is that right? Have I done that right? X plus. Oh, sorry, I'm doing the wrong one. We're trying to differentiate 5 over 2. So I do x to the 5 over 2, x to the power of 5 over 2, and differentiate at x equals 4, and it should tell you the answer is 20. So has everyone seen that they can do that on the calculator before? So check that out if you didn't know you could do that. But at the end of the day, like I said, when it comes to the exams, you have to show how to do it. It's just nice to know that you can check it potentially. That only is true for when you're subbing a value in. Otherwise, you have to just be able, you need to just differentiate it, and the calculator doesn't do it. Right, sorry, that was my mistake. If you just got 0.8125, I think I said the wrong thing there. I differentiated this. The question here was x to the 5 over 2, wasn't it? But I should have put that. So you need to do x to the 2.5 or x to the 5 over 2 at x equals 4. Oh, fair enough. Either way, whether you have the calculator, whether you're allowed to use the calculator or not, you need to be able to do this skill without. So that's what they're going to test. They're going to check the work in a method. So don't worry at all. Yes, that's it. So differentiate with respect to x. So let's do these quickly. 5a, this will become 4x cubed plus, and remember that this is 6x to the half. So that will become plus a half times 6, so 3x to the minus a half. And then differentiate this. So for part B, I think I would first of all expand it as x squared plus 8x plus 16. And it's all being divided by x. So if I differentiate that, that will give me that d dx of that. Let me write that up there. Derivative of all of this is equal to, well, that will cancel. And so we're effectively differentiating x plus 8 plus 16x to the minus 1. So when we differentiate it, we get 1 minus 16x to the minus 2. That's the derivative. And well done if you got that. Yes, brilliant. Well done. So hopefully you guys got that okay. It looks like some of you worked that through perfectly. That's lovely. So that was really good. And thank you for taking part so well, asking so many like good questions that follow this up. For those that asked about the graphs, so the skill with the graph of knowing that x squared, the derivative is 2x, you can draw tangents on, find the individual steepnesses, and plot the gradient function on the same graph. That's a very different skill that finds the same thing. So it is good to look at that in terms of graphs. I would also recommend, guys, if you look on, there's like lots of free online graphing software like Desmos and GeoGebra, where you can type a function in and then put like fx equals this, f dash of x, and press enter, and it will draw the gradient graph. It will draw the derivative as well for you. So there's that kind of, to know that that works is quite good. Just to talk quick about the other web classes we've got and the other resources we've got on Snap Revise. that might be really helpful. Obviously, rounding this off, we've looked at a derivative as being the thing we get when we differentiate. We've differentiated some polynomials, and we've differentiated some harder polynomials as well in light of exam questions. So if you have any questions, do feel free to keep them coming. What I'm going to do now is briefly just talk about Snap Revise. So obviously we have upcoming web classes on the Sunday, much like today. So please set a reminder on YouTube. Yes, it is absolutely a skill we need in terms of graphs, but a lot of the time the questions don't have the graph drawn because they're looking for you to find the equation of a tangent or do something with it. But it is very much tied in with graphs. So there's so many different styles of questions that could come up. So yeah, it is. That's lovely to hear. Just to quickly just let you guys know, so the Snap Revise courses, there's a lot on the platform that would hopefully really help, and it is all really clearly set out. And the one thing I would say that's been lovely about the Snap Revise platform and all the resources on there, especially at this time where the A-level and GCSE have changed so much, is that it's, aside from being very clear and really kind of beautifully laid out, it is bang on and up to date with the newest kind of syllabus. So a lot of the other sites that you'll use for resources, there's an abundance of maths practice questions online, but the good thing with the course is they are all tailored to the exam board, to every sort of specification point, bang up to date. So you're not kind of practicing something that's out of date, and you're not going to miss things. Everything in there that's on the course is really clear and easy to revise, with like a lot of different interactive options on the platform. So the web classes, the drop-in sessions, the flashcards, there's loads on offer. So just going to just talk briefly about that, and lots of little videos that kind of break it down to a bite-sized level, so that you can just quickly learn the thing you need help with, and then diagnostic quizzes and so on. So the revision materials are superb, but also just to help you kind of learning the stuff. There's loads on there. So this offer I mentioned, the Back to School 21, will give you 25% off the first month's subscription. So if you want to try it out, see if it's working well for you, this code's going to expire in 48 hours, but I'll show you on the site what to do and talk this through. So if I just stop sharing that momentarily, and I'll share the website. So if you haven't been onto the Snap Revise website before, this is it. So there's loads going on here. The courses, we've got the flashcards are really lovely and designed for all the A levels, every point, questions and answers. You can really sort of Snap Revise is kind of in the name. Nice and snappy revision that takes the whole A level and lays it out really in a nice, clear and coherent way. So that's worth knowing. But the courses is really what we want to have a little look at. So if you want to start the free trial, and then obviously we've got the promotion code I mentioned earlier, please look at that, because there's a lot on there. So what we've got, for example, for maths, we have the drop-ins and web classes. So for example, for maths, Monday and Wednesday, I'll do A-level web classes followed by a drop-in. So the schedule is on here. As you can see, all the September ones with a catalogue of ones that you might have missed if you'd like to go back and watch them, and all the upcoming ones for October and so on. So for example, on this date, I'm going to be looking at combinations, and we do all of the pure maths, the mechanics and the stats. The whole A-level is covered in a kind of timely fashion with what most schools and colleges will work through, and kind of organized in the same way. And after each session, there's drop-ins, so you can ask about any work you need help with. But there's a lot more on the courses than just the web classes and the drop-ins. So aside from the support you're going to get, you've also got the diagnostic quizzes, and everything else that, as I mentioned, the revision packs, the exam practice questions. So I'll have a little look at showing you, for example. So for the maths, the course we've got, I'll just go back, because obviously we've got the promotion code on there. You can look at the quizzes, you can look at the diagnostic quizzes, but also the little snippets and the videos, and the diagnostic quizzes will jump you specifically to the bit you struggled with, and then you can answer questions on it and follow it up. And yeah, it's just a very interactive platform with loads of resources on, as I said, tailored to the exam board and the syllabus that's bang up to date. So please do check that out. And as I said, the code is there. I think it's in the chat. So please do have a little look at that. And yeah, as I said, do set reminders for the YouTube sessions, which will be coming up. I'm just going to see. Yeah, so I'll stop sharing that there. If you do have any questions, let me know. But as I said, that code is there in the chat if you'd like to check that out, and set a reminder on YouTube for the upcoming sessions. But it'd be great to see you at the web classes. So if you do want to join, see what it's about, and see kind of, hopefully this has been useful today. But as I said, we go through the whole course, and there's a lot more on the platform that's kind of interactive and allows you to take ownership of your subject and the bits you're studying as well. So it will allow you to focus on the specific bit that you need to practice, and really kind of tailors the content towards you. So hopefully that's been useful. I hope you all keep well, have a good week. And yeah, thanks very much again to everyone for the comments and the questions as we've gone through. Take care, guys. Thanks very much again. And hopefully see you at a session at some point soon. That's great. Take care. Thanks, guys.